So we finally made it to one of my favorite lessons of the year in calculus class. And unfortunately, I can't be there to talk to you about this in person. So in place of me, I'm knocking out this awesome 2020 quarantine dark mode version of my lecture. 2020 2022. It's 2022 already? Holy cow. 2022 quarantine. Dark mode. Smiley face. Okay, now before we talk about the fundamental theorem of calculus, I have to make sure that you have a few concepts in place that we've discussed prior to getting here. So let's knock it out before we move on to that. First of all, I want to make sure you remember antiderivatives, and I want to clarify just some notation issues to make sure we're on the same page. So, oops, I just made some dots there. Let's erase those. So remember that an antiderivative is kind of like a Jeopardy game for derivatives. We give you the answer or the derivative, and you work your way backwards to figure out what the function was. And there's notation that goes along with that I just want to make sure everybody understands. So first of all, let's say that we have a function like f of x equals x squared minus 4x plus 7. And if we want to find the antiderivative of that function, we have some special notation. The notation that we're using looks like this. It's a little integration symbol. We put the function that we want to find the antiderivative of. Oops, that's a minus sign, not a plus sign. We got to get that right. And then we put the dx on the end. Oops, close the parentheses there. So remember these symbols here, this integration symbol and this differential. Right now, those are just notation that tell us, hey, we're going to do the antiderivative. And we use that power rule that we learned to figure out that the antiderivative is x cubed over 3 minus 2x squared plus 7x. But remember, we've got to stick this fancy plus c on the end. That constant takes care of all of those parallel functions that occur in the plane that have the same derivative, right? So there are an infinite number of functions that have the derivative x squared minus 4x plus 7. Now, I want to make sure you understand how these pieces are named. So this part right here, this has a special notation. That's called capital F of x. The antiderivative part that we can figure out is capital F of x. And then remember, we've got that constant that we put on the end. So in general, if we are doing an indefinite integral of f of x, the answer is the antiderivative plus that constant c. And this capital F represents that antiderivative work that we did right here. Okay? So capital F has a role there. If it's lowercase f in the function, we use capital F for the antiderivative part. Okay, we're going to need that later, so that's why I brought that up. Let's move on. So the next thing that I want to make sure you have a clear understanding of is the notation for what we call definite integrals. And so, ooh, I guess I can't do that. Yeah, we need this. Okay, so sorry, I'm talking to myself about this app. Let me draw a little picture here. So let's say we have our coordinate plane. We're just going to deal with the first quadrant right now. And we have a function f on a closed interval. Right? How's that look? Not bad, right? And this left-hand boundary is marked on the x-axis by coordinate A. And this right-hand boundary is marked on the x-axis by coordinate B. And the area under the curve is what we've been trying to figure out, right? We're trying to figure out the exact area of this region. That's called a region. Well, the other day, I let slip that this thing has a special notation. So we don't have to write out that limit of the sigma Riemann sum thing, right? The area here, this area, can be better and more concisely described as the definite integral from a to b of f of x dx. Right? If this function is f of x, which I haven't labeled correctly, but let's just say this is f of x. If this function is f of x, we can identify that green area with this notation instead of the Riemann sum notation. Now, as of this moment, the only way you know to compute this area is with that limit of the Riemann sums, which is impractical. It's a hassle. It's full of algebra that trips people up, and it's not very efficient. So today, we get to talk about how we can quickly compute these definite integrals. Excellent. That lays the groundwork. We know about antiderivatives. We know about definite integrals and how they represent the area. Now I just need to show you the relationship. So let's talk area. Let me redraw that little picture I had. Remember, we've got a function in the first quadrant. We're going to call it f of x. It's entirely in the first quadrant there. We have a boundary for the region under that curve, starting at x-coordinate A and ending at x-coordinate B. And I'm going to shade the, actually I'm not going to shade any area right now. So let me just label this thing so we know what we're dealing with. This is f of x. This blue function is f of x. Now what I want to do is make a new function, all right? A new function called a of t. The way we usually say that in mathematics is we say let a of t denote the area of the region. That says the, by the way. Pretend I'm not writing sloppy. Under f from x equals a, which is the left boundary, to x equals t, where t is between a and b. So mathematically, we write that like this. Sorry. A is less than or equal to t is less than or equal to b. So I'm throwing this new variable at you. Let me show you where it is on the x-axis. It's between a and b. So for example, what if t were right here? Okay, that's t. And then a of t is the area here of this region. And the idea is I can slide t anywhere I want in that interval. Okay? So I've got a little animation here I want to show you, and then we'll come back to this picture. So I made this little presentation on Desmos, and I'll share it with you, the link, when it gets to that point. But essentially, oh goodness, I need this. Okay, here. There it is. Okay. So essentially what happens is I set the slider up so that as I move t along, the area of the green region changes, right? Notice if I move t all the way over on A, there's 0 area, and that's going to become important. So remember that. When t is at A, there's 0 area. And when I move it all the way over to the other end, when t is at B, it's the entire area under the curve. Anywhere else in the middle, it's just a portion of the area, right? So you can see how that slider determines the area. And it's a little easier for me to recreate that here than for me to try and draw a bunch of different pictures where I move t around. So you're welcome for that. But from this slide, we want to make sure we just make a note that the area when we're all the way over to the left is 0. And the area when we're all the way over to the right is the complete area under the curve. Okay. So you can play with that if you want. It's going to come into the rest of my discussion here, so keep that in mind. All right, let's move back to that slide we were on. So here we are back at that slide, and let's just make a note of the things we noticed when we were looking at the Desmos. First of all, we said that if we set t equal to a, in other words, I move this t back over here all the way so it's on a, there's no green area. So what that implies is a of a equals 0. Now, remember, we know that we can use definite integrals to represent area. So another way to write this is that the definite integral starting at a and ending at a of f of x is 0, right? Because this a function is just the area under that curve. And so this is how you denote the area under f of x, starting at a and ending at a. So that's a neat little piece of information, that when these two numbers are the same, the answer is 0. We just figured out how to solve our first definite integral. Okay, the other thing that we said is if I move t all the way over here under b, that would be a of b, and that equals the entire area. Now, I don't know the answer to that right now, but I do know that that definite integral would look like this, starting at a and ending at b of f of x dx. So this is going to come into play later. Right now, though, keep in mind, we do not know the value of this area. Okay, that's what this whole video is about, trying to figure out what this means, what the answer is, right? What the value of the area is. Okay, so those are two notes from that last slide. All right, now let's attack this area thing. So what I'm going to do is I'm going to put my picture back here, and I'm going to introduce another variable to this thing. Oh, I should have just left the picture here. Sorry, I got to redraw it. So here's my f of x, and here's my a, and here's my b, and I'm going to put t in right here. Okay. Now, what I'm going to do is I'm going to move t from its current position over this way a little bit. I'm going to move it over a distance of h. That's an h right there. And that means this new coordinate right here would be t plus h. Okay, so let me use two different colors here. The area from a to t, I'm going to make green. That's this guy. And the area from a to t plus h is yellow. It's all this. And truthfully, what I'm really interested in is the area right here from t to t plus h. So let's see if we can figure that thing out. Okay. So that red area right there, and I'm just going to call it red area for now, is going to equal a of t plus h, right? The yellow area. And let me make that in yellow. This is, might as well, if I got all these colors, I might as well use them. Do something right for once. Okay. So a of t plus h, that's the yellow part, minus the green part, a of t. That's the red area. All right. That's the area from x equals t to x equals t plus h. Right? That's this area. Let me use a red pen here. That's this area right here. Okay. The red area is a of t plus h minus a of t. Okay. And I'll even clear up, let me just clear up my picture. I want to make sure I don't miss anything. So if you take out the other stuff, then what we've just found is this. Just want to make sure I don't leave anybody behind. That is not my goal. Here's our F, here's our A, here's our B, and then here's our T, and here's our T plus H. I'm writing it a little wide, but really H is pretty small. And this region right here, that's A of T plus H minus A of T. Right? That's this stuff. Okay. All right, now, here's where we're going to have to make an approximation. If we were estimating that area, we would draw a rectangle, and it almost looks like a rectangle. The thing we'd have to do is we'd have to decide how tall to make it. I know how wide the rectangle is. It's h. What I don't know is how tall it is. And remember, when we made our Riemann sums, we decided that choosing the left-hand endpoint made the right-hand endpoint, excuse me, the right-hand endpoint made the math the easiest. But in this case, because I have t on the left and t plus h on the right, I actually think choosing the left-hand endpoint makes more sense. So my height for this thing, I'm going to call f of t. That's easier than f of t plus h. Okay, so the approximate area, if I just made the rectangle here, right, if I do this white rectangle, the approximate area would be h, the width, times f of t, right? That's the approximate area. And since I know the real area is a of t plus h minus a of t, I can write a new equation. I'm going to write that in right here, and then we'll start a new slide for the math. So the real area, a of t plus h, that's supposed to be a of t plus h, sorry, minus a of t is approximately h times f of t, that's our rectangle. And that equation is what's going to get us where we need to be. So let me start that on a new slide, and we'll pick up where we left off. Okay, so here's that equation we had at the bottom of the last slide. Now, what I want to do is just a little quick bit of algebra here. I'm going to divide both sides by h. And when I do that, I get the following. A of t plus h minus a of t over h. Ooh, my h was white, wasn't it? Over h is approximately f of t. It's approximately f of t. Now, here's where I'm taking a leap of faith. I'm hoping that you'll recognize that this bad boy is a famous fraction. Hopefully that bad boy looks familiar, because that was the basis for everything that we did in the first semester, right? So drum roll, please. I don't know how to roll my tongue, so just pretend I made a drum roll. Let me write out what this thing is. This is the difference quotient for the function a of t. And we know that when you take the limit as h approaches 0 of that thing, you get the derivative of a. So a prime of t, is exactly equal to the limit as h approaches 0 of this difference quotient, a of t plus h minus a of t over h. That's a doggone fact, right? And so I can take this a step further, and I can say, as h goes to 0, right? As h goes to 0, a prime of t equals f of t, right? Right now, this is approximate, this relationship here. But if I send h to 0, it's going to get right into f of t. And I know that because of the picture, right? I'm not making that up. Let's go back to our picture. I'm going to sketch it quickly. If h is 0, t and t plus h are in the same place, right? So here's a, here's b, and here's t. And remember, h is the distance between t and t plus h. But if it's 0, t plus h is the same. Okay? And that means that we already said this was f of t. So this becomes true when h goes to 0. All right, now what that tells us is that the derivative of a is f of t. The derivative of this function a that we made up is f of t. And we have notation to describe that. So new slide, new notation. Okay, now remember when we had that discussion about antiderivatives? If we take this a prime of t and we work backwards, a of t is one of the antiderivatives. So that implies that a of t, right, we're working backwards from the derivative, plus some constant, and actually I'm going to call that c sub a, will equal the antiderivative for f of t, which we've already said was capital F of t, plus some other constant. I'll just call that plus c sub f. Now what typically happens is we combine these two constants. So I essentially subtract this c of a over, or c sub a over, and I say the statement like this: A of t equals capital F of t plus some constant. Now, C sub f, the constant for the right side of the antiderivative, is all of the possible real numbers, and C sub a is the constant for the left side, and it's all the real numbers. So unlike algebra, when you add these two things together or when you subtract them, you still get some other constant. So we typically just write plus C on there. Okay. Now, this statement we're going to use to help us solve for C. Because from the last slide, remember, I have some information. I know that A of A equals 0. So if I plug A into this function, that would be A of A equals F of A plus C, right? And since A of A equals 0, I can substitute 0 here, right? I can put this in. And when I solve for C, I get C equals negative F of A. Okay, that's great news. So now I know what C is. Okay, now here's the kicker. Let's do A of B, which is what we're really trying to find, right? We are trying to find the area under that curve. So remember, I'll write in yellow here. A of B equals the definite integral from A to B of f of x dx. Okay, so remember that. Because A of B, from this green equation, A of B is just capital F of B plus C, right? I'm just coming down from this one and plugging B in. And since we know A of B equals this thing, check out what we get. Definite integral from A to B of little f of x, that's lowercase f x dx, equals f of B. And then remember what we just said C was, minus f of A. And believe it or not, that bad boy is one of the parts of the fundamental theorem of calculus, and it's the one that's most useful for calculating the area under the curve. So that's a big deal that we made it there, and there was a lot of stuff going on. But essentially what we've just figured out is if you want to find the area under f of x between endpoint A and endpoint B, right, the entire area here, exactly, without doing Riemann sums, you just do the definite integral from A to B of f of x dx. That's what we write. And the way you calculate it is you figure out the antiderivative with B plugged in and subtract the antiderivative with A plugged in. Notice we don't need plus C here. This is just the f part of the antiderivative. It's not the plus C part. So just the expression that you do by using our rules. That's a huge deal. Okay? All right. Let's wrap this up and show you how to use it on the next slide. So here it is, the fundamental theorem of calculus. All the stuff that you sat here listening to culminates in this equation. That if we want to know the area under a curve from A to B of a function f of x, we represent that as the definite integral from A to B f of x dx. And we now know that that value is capital F of A, of B, sorry, I wrote it backwards. It's got to be B first. Capital F of B minus capital F of A, right? We replace the C with that. And this stinker is one part of the fundamental theorem of calculus. Now, our textbook calls this part 2. Part 2 of the fundamental theorem of calculus. Some other texts might call this part 1. We'll talk about part 1 in a different discussion. We actually blew past it as we were working our way to this. But this is the guy that shows us how to compute area without having to do those Riemann sums. So let me show you one quick example and then let you try and knock out some problems. All right, let's say we want to find the area underneath the function 3x squared on the interval 0, 2. Instead of setting up delta x sub k and c sub k and f of c sub k times delta x sub k, all we need to do is figure out the antiderivative and plug in our two values. So let's get organized. In this problem, remember a is 0 and b is 2. And we need that capital F. that would be the antiderivative of 3x squared, which is 3x cubed over 3, better known as x cubed. So if you want to find the area under this curve, you just need to take that f of x, right? The c we don't need to worry about, that function, and we need, oops, that's a cube, sorry. And we need to plug in capital F of b, so f of 2, and f of 0, and subtract those. Now, the way we do that is with this notation. We say, hey, we're going to figure out the antiderivative without the plus c, which is what we have over here, x cubed. And then to indicate that we're going to plug two numbers in, you put a straight bar, not a squiggly integral bar, a straight bar, and on the right side, you put your two numbers. So the number 2 goes in first. This is first. Then the number 0. And the calculation that we have is 8 minus 0, which is 8, and that's square units. Or units squared, right? Because this is an area. Okay. You do the antiderivative using those rules. You write it down without a plus c, and then one at a time. First you plug in b and get that answer. That was 8. Then you plug in a and get that answer. It was 0, and that was our value. That's the area under the curve. If you did this problem with Riemann sums, you would get 8, but it would take you about a page, and we did it all in one line, plus some extra organization notes here. So that's the fundamental theorem part 2 in a nutshell, and this is the thing that saves us from having to do Riemann sums whenever we want the area under a curve. And so what we'll do for the next couple of weeks is we'll just play around with these definite integrals and find out all their properties and practice computing them so that we can use them to solve some really awesome problems. Okay, that's enough for this talk. My voice, I'm about ready to cough right now. Excuse me. Losing my voice a little. I do miss you guys, and I hope to see you soon. In the meantime, do some definite integrals and calculate some area under the curve. Take care.